Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson for intermediate thermodynamics, we'll be continuing our discussion of multiple reactions, but this time adding in the complication of multi-phase or heterogeneous reactions. So we know that at fixed temperature and pressure, chemical equilibrium says that I'm going to, for the sum of all components, have the stoichiometric coefficient for a particular reaction times the partial molar Gibbs energy of each species add up to 0 for every possible K for my possibly M reactions. And phase equilibrium, we've seen that previously. We know that the partial molar Gibbs energy for a species in any pair of phases will also be the same. So for every species I and pair of phases alpha beta. The practical way we use these is that we say that chemical equilibrium results in equilibrium constant based on activities for reaction K is the product of all components activities raised to the stoichiometric coefficient power for every reaction K. And the phase equilibrium, how we have learned to use that is by saying that the fugacity in the species or in the mixture for a particular species in each phase will be equal to each other. So let's consider a reaction. Here I have a liquid and a gas that react to form a liquid and a solid. This reaction will occur at 25 degrees C, and the delta G of reaction is known to be 3.1 kilojoules per mole. Now in this case, A and C will only be in the liquid state. They will not tend to form a solid or gas. And B would only form a gas and D would only form a solid under the conditions that we might be interested in. And we can find the equilibrium constant. Ka is the exponential of negative delta G reaction over RT, remembering that I need to make sure that these units all cancel and that my temperature is 25 degrees C or 298 Kelvin. And in this case, Ka at 25 degrees C is 0.286. I also know that chemical equilibrium tells me that this 0.286 is equal to the activity of species C times the activity of species D over the activity of A times the activity of B. Now, if I don't make any assumptions about the pressure or anything like that, just simply looking at what type of material these are, this says that 0.286 is equal to the activity of C, which is a liquid, so it's X of C, meaning liquid phase composition, times an activity coefficient times an exponential term. And for the gas, or for D is a solid. I was doing the wrong side there. D is a solid. For that, it's 1 times the exponential of a very similar looking term. But remember, for solids, we use the pure molar volume. And the vapor pressure I can use is doesn't really make sense, so it's 1 bar is the pressure there. In the denominator, I have species A, which is also a liquid. So XA over gamma A exponential and finally I have B, which is my gas, and that's going to be Y for B times the pressure times the fugacity for species D, and that's D, in the mixture. We didn't specify the pressure, but if I make an assumption that the pressure is low to moderate, then these exponential groups can be eliminated as being very close to 1. And in the denominator, phi, the fugacity coefficient, will be very approximately 1. And so I end up with this as my approximation for low to moderate pressures. If A plus C form an ideal liquid, then gamma of A and gamma of C will be 1. And so this is 0.286. X is equal to X sub C over X sub A, Y sub B, P. So let's continue with this thought by considering a feed that is 1 mole of A and 1 mole of B. And in this case, I have N sub A is going to be 1 minus my extent of reaction. N sub B will also be 1 minus X. N sub C is just X, and N sub D is also just X. If I look at the total number of moles from this reaction, there is no change, so started with 2, end with 2. However, I have gases, and the only gas I have is B, and so therefore the number of moles of gas will be 1 minus X, and the number of moles that will be in the liquid are going to be N sub A plus N sub B, which means that's going to be steady at 1. Therefore, X sub A, because it's in the liquid phase, is 1 minus X over 1. B is in the gas phase, so Y sub B is going to be 1 minus X over 1 minus X, which is equal to 1. X sub C will be X over 1, liquid phase. And finally, I don't know, what do you want to call it, a W sub D? The composition of the solid is just identically 1. And if we substitute those in, therefore, we end up with 0.286 is equal to, that's an X, over P times 1 minus X. Now we can rearrange this and solve this. And if we play with this and set P equal to 1 bar, we find that X is equal to 0.4. And when P is 1.5 bar, we find that X is 0.75. And so far all these answers are making great sense. But now then, let's try P equals to 2 bar. And in this case, I get X equals 1.34. That's greater than 1. That's not possible. So what does this even mean? Well, the problem is that as I proceed with this reaction, P is going to be likely to change. I'm going to have to continually shrink down the volume to keep up with the pressure needs as the gas disappears. And this becomes a particular problem because we've made sort of this assumption that the liquids and the solids take up essentially no space in the volume. And so therefore, the pressure is all due to the gas. But once the gas disappears, what? There's nothing else to happen. So therefore, one thing you can do is say that you fix the volume instead. And if we assume an ideal gas, I mean, you don't have to assume an ideal gas, but it's just easy to show you very quickly what happens. P is nRT over V, and N, this is for the gas phase, so that's the number of moles of D, and so therefore it's 1 minus X times RT over V. Our expression, therefore, really, in this case, holding volume constant, becomes X over 1 minus X, square that, times RT, and a V. This is for a fixed volume. So now, what if we consider ideal or non-ideal liquids? We can choose any of our models for activity coefficient, but let's just use a one constant Margulis equation. So let's say that gamma sub A is the exponential of A x sub c squared over RT, and gamma sub c is the exponential of A x sub A squared over RT. Now A is a constant, and we would determine that from phase equilibrium data. If you want to give it a number, A equals 0.1. There you go. Now you have a number to plug in. And so, therefore, this is going to really just be a function of our compositions, or in this case our conversion, x squared over 8.314 times 298, and this is the exponential of 0.1 times 1 minus x squared over 8.314 times 298. When we plug these in, we get 0.286 x times the exponential of the 0.1, 1 minus, that's a 1, minus x quantity squared over 8.314 times 298, all over p times 1 minus x exponential of 0.1 x squared over 8.314 times 298. We can work with the x over the p times 1 minus x, or we can use our ideal gas law if we want to fix volume. If I fix the volume, then 0.286 is equal to x times v over RT 1 minus x squared. And then all of these exponentials, I can just subtract the exponents. And I end up with this. Now this is highly nonlinear, but it still could be solved using a computer aid of some sort to solve this numerically. And finally, what happens when, let's just choose B and C can form both liquid and vapor. So one binary mixture, I have a choice of which phase those two are going to be in. So what's going to happen is in all of the previous work, I can no longer say that I know Y for my gas, B, or X for my solid or my liquid, C. I can't get that anymore. I don't get them from the material balance. The material balance still matters, but it isn't sufficient to get this information. What's going to happen is I now have two new variables, right? I've added two variables. And so therefore I need to have two new equations. And my new equations come from the phase equilibrium relations. If I assume that they form an ideal mixture, and I can use Raoult's law or maybe a modified Raoult's law, then these become my additional equations. So now I have a system of equations that are nonlinear and must be solved simultaneously along with my XA expressions. So this is something that this is when going to Aspen Plus is usually your best bet, but you also can write software to solve these things. So this concludes our little glimpse into what happens with heterogeneous chemical reactions. Thank you very much.